All right, so if you have any questions about the problem set, I'd be happy to answer them in office hours or after class. So there's, I can't really say anything about them generally because all the problems are different. There was a lot of very unsafe things going on in these problems. But somebody had a carousel where a passenger would be feeling 1,000 G's of acceleration. But I didn't mark off for that kind of stuff. Yeah, right. No, that wasn't really. Yeah, exactly. But yeah, feel free to come, talk to me about questions. I'll post the new problem set soon, today or tomorrow. Kenny noticed something on one of the assignment problems. It was the first problem. I think it's listed as number 2 because the first one is just reading through the notes and stuff. But it was a linkage where you had two members like this connected by a pin joint, a frictionless contact over here. You had some things were specified about the angular velocity. And there were some external forces applied. I think there was one here and one here. And if you do this problem, you get that. So there's an issue, and that is that you calculate a normal force with the ground that's negative, and that doesn't mean anything. I wanted you to use that constraint, so let's just, the way to fix this is just to change the problem, and I'll change this on the document too. So that's a pin joint, that's a pin joint, but down here, just make that a pin in a slot joint. It doesn't change anything about the problem except that now that negative normal force is realistic. Yep. So yeah, that's the next thing I was going to say is, if this was really the system that you were dealing with and you wanted to know what was going on, you would go through all the steps, assuming that there was contact there, calculate that there was no contact, and then that means that that point is accelerating away from the floor. That's totally fine. I mean, this system can do that. So then at that point, you would do the problem again without the floor there at all. With no normal force, and you'd have to go through it twice. But what you would get the second time is that when you went through Newton's laws. Okay, so what's going to happen when you do it the first time through with this or with the new formulation? You're going to get one equation from Newton's laws for this member because it has a fixed point. You're going to get 3 equations for this one because it has no fixed point. So you have 4 equations from Newton's laws. But you have 7 variables, so you need 3 constraint equations. 2 of those come from the acceleration at the pin, and 1 comes from the acceleration at the pin and slot. Because you don't know anything about the x acceleration at that point, but you know that there can't be any y acceleration. So that's what you're going to do in the new problem. But just for, if you're curious about it, if you were definitely dealing with this system and you calculated that there can't be any normal force with the floor. Now you'd go through again without the floor there. You'd get one equation from Newton's the rotational equation for this member, 3 more for this member. So you'd have 4 equations again, but this time there'd be no normal force. So you'd only have 6 variables, 4 equations, and so your only constraint equations would come from the acceleration at that point. And then you could solve it. But just do it like this. Any questions about that? All right, so last time,
Question.
yeah.
When you post grades for like stuff on D2L, why doesn't like give any notifications? Like it doesn't even show that you posted something, like you updated the grade or something like that. Like even D2L itself on your computer doesn't show like the red dot that you added grades or something.
Yeah, I can actually
Like-
back that up like you do on mine.
It doesn't what? Give notifications?
You actually did to the grade book. Like you did, either you posted the problem set scores or like quizzes.
Uh-huh.
It doesn't even show like until this morning. I didn't even know
like
that
the
you had
right-hand side when you walk in has like that little red dot.
Oh,
the
So
notification.
it doesn't show up on there that things have been added.
oh. But if you go to the grades, it's been updated?
Like it would show,
But it just doesn't give you a notification that anything's been added. That's weird. I mean, I didn't know there was a notification in the first place, but I can't answer that question.
Other courses will give me notification. I've made no adjustments to how I receive notifications in D2L. It's just the one, however.
Only my class.
Right.
Okay, well, I'll look through. Maybe there's some setting that I missed that notifies students. I'm sure there is. I'll look through it. Weird. It's funny when you, because I know there have been other classes where students must have been getting notifications, because I've had ones where it's like I'll have different lab sections of the same class, and I'll enter the grades for the first lab section, and before I've gone to the second lab section, so it, like we're talking about 3 minutes or something, in that 3-minute gap I'll get emails from students like, I got a 0 on this, Okay, so last time we started talking about kinematics and kinetics of particles. In rotating coordinate systems. And we got this, well, we didn't get it. I gave you this sort of crazy result. Well, first let me remind you what the issue is. The issue is if the coordinate axes, okay, so, sorry, let me word this a little differently. If you take a time derivative of a vector ux times I plus uy times j plus uz times k, you get ux dot times I plus uy dot times j plus uz dot times k plus ux times I dot plus uy times j dot plus uz times k dot. And that's nothing complicated. That's just the product rule. When the coordinate system axes are not changing orientation in time, then all this stuff, the ux times I dot plus the uy times j dot plus the uz times k dot is equal to 0, because if I, j, and k aren't changing, then their time derivatives are 0. But in a rotating coordinate system, we have to deal with those terms. These terms are non-zero. And the way we're going to think about it, you can think of those terms as correction terms. So you can calculate d dt of a vector like you're used to doing it. Then add the correction term. And what's the reason that we need to do this anyways? Why not just, why not just calculate our time derivatives relative to our rotating coordinate system? What's the issue there? That might not be a very well-worded question. Yes, exactly. That's the way that I drew it up with that astronaut example. So the idea is you can't use those accelerations, those kinematic quantities relative to the rotating coordinate system, because that's a non-inertial coordinate system and Newton's laws don't hold. And the main reason that we're going through these calculations is to set ourselves up for Newton's laws. Okay, so we need anything that's in a non-inertial reference frame, we need to correct it so that it actually gives us a value in an inertial reference frame. Okay, that's the idea. We're correcting everything so that it's an inertial quantity so we can use it with Newton's laws. And I gave you this surprising fact at the end of last class, that this correction term, ux times I dot plus uy times j dot plus uz times k dot is equal to the angular velocity vector crossed with the u vector. And it doesn't even matter what that u vector is. Any vector, if you want to express, if any vector that's measured in a rotating coordinate system, this relationship holds. So if you want to calculate the time derivative of any vector u, that's equal to ux dot, uy dot, uz dot plus omega cross u. So you can think of that as, I just keep writing this a couple different ways. So ux dot times I plus uy dot times j plus uz dot times k plus omega cross u. Okay, so that's kind of surprising. Okay, it's a surprisingly simple way to calculate these correction terms. So where does that come from? Maybe you don't care. That's probably the correct attitude, is not to care, just use it, learn to use it right. But I'm going to go through a little demonstration in 2D to show where that comes from, because I'm sure, surprising results like this, you sort of tend to be sort of naturally curious about it. Why does that work? Well, the correction term is, how many times am I going to write this today? That's the question. Yeah, ux times I dot plus uy times j dot plus uz times k dot. The meaning of ux, uy, and uz, that has an obvious meaning. The question is, what are I dot, j dot, and k dot? That's what's not so clear. So let's think about them we're going to do this in 2D. This same approach works in 3D, but you have to think of angles, like it gets complicated. It's easier to think of it in 2D and just convince yourself you believe that this is true. So and you know what? Let me change some notation here. Sorry about this, but instead of thinking of that as little lowercase omega, the way that we've been thinking of the omega of a rigid body, now we're talking about rotations of a coordinate system. Okay, we want to keep those separate in our mind. So let's call this uppercase omega. So that's the angular velocity of the coordinate system. Okay. Just to keep straight in our heads that there's a difference between the coordinate system rotating and a rigid body rotating, or a particle, moving through an angular rotation. Okay, so think of this in 2 dimensions. With the coordinate system rotating in time about the z-axis. Okay, so this is the coordinate system at instant 1. I'll call this, so this is the I-axis at time t. And this is the j-axis at time t. What happened to all my toolbars? Oh well. Okay, I'll just do it all in black. Okay, so then this is an exaggerated rotation from the coordinate system at time t to the coordinate system at time t plus, let's call it dt, to emphasize that this is an infinitesimal amount of time. And this is j at the instant t plus dt. So obviously this angle would have to be infinitesimal too, but I'm just drawing it out so you can visualize it. Then let's call the angle from t to t plus dt an infinitesimal angle d theta. And I'll put a z here so you remember that's about the z-axis. This is also d theta z. And then this vector here is di. That's the change in I. To get the second I vector, you add the original I vector plus di, and you get this. And this is the vector dj. Any questions about that so far? All right, and here's something weird. For a finite rotation like this, these are isosceles triangles, no right angles. But as you take the limit towards an infinitesimal rotation, d theta, these angles both tend towards right angles. So I'm going to treat this isn't really like careful limiting procedure, but it works if you do it as a careful limit. You just have to take my word for it. So I'm going to treat this like a right triangle. And intuitively, it should make sense that as that angle goes to 0, this approaches a right triangle. Same thing here. Okay, so let's figure out how we can represent what's the relationship between d theta z and di. Well, this is a coordinate system. These are coordinate axes, so the length of this and this and this, they're all equal to 1, right? So this vector di is equal to the hypotenuse of this right triangle times the sine of d theta z. And what direction is that pointing in? This gives you the magnitude of that vector. What's the direction of that di vector? Positive y, yep. And since this is infinitesimal, sine of d theta is equal to d theta, right? That's a small angle approximation. And so you get d theta z in the direction of j, so d theta z times j. And now take divide both sides by dt, and you get that di dt, the thing that we're looking for, is equal to d theta z dt times j. What's d theta dt? Like, just think about the definition of the angular velocity. This has to be equal to capital omega in z times the j-axis. And now let's do the same thing for the relationship between d theta z and dj. This is the vector dj. The magnitude of that vector is the hypotenuse of this right triangle, 1, times the sine of d theta. It's the same procedure as before. And what's the direction of dj? Negative I. Yep, exactly. Small angle approximation gives you that this is equal to d theta z times I, and it's in the negative I direction, so negative. And so the time derivative of j is equal to negative d theta z dt times I, which is equal to negative capital omega z times I. The 2D correction term is ux times I dot plus uy times j dot. And so using these formulas that we just figured out, that's equal to ux times capital omega z times j minus uy times capital omega z times I. And that's equal to this omega vector crossed with the u vector. So that simple form for the correction term comes from the relationship between those time derivatives of the coordinate axes and those infinitesimal angles. Okay. Yeah, and it works out the same way because these are infinitesimal rotations that we're thinking about. If you're doing finite rotations, you can't think of, it's more complicated. But for infinitesimal rotations, you can think about it the same way. So yeah, this is just a 2D, hopefully like sort of intuitive demonstration of why this works. And then you just have to take my word for it on the more complicated one. Okay, but we're often going to be doing it in more than 2D. Okay, so so this is the major result for rotating coordinate systems. For any vector u expressed in a rotating coordinate system, expressed in a coordinate system rotating with an angular velocity omega, capital Omega, the time derivative of u is equal to the time derivatives of the components plus capital Omega cross u. Another way to think about that, so let me box this one. Is that the time derivative of u is equal to the time derivative of u observed in the rotating coordinate system So like if you're taking these measurements in a rotating coordinate system, this is what you would think, this is what you would see, this is what your measurements would tell you, plus the correction term, capital Omega cross u. Okay, these two are the same thing. This u dot observed in the rotating coordinate system means you're just taking the time derivatives of the components. All right, so what's this good for? The main use for us is in calculating velocity and acceleration vectors. So we're going to apply this formula to a position vector expressed in a rotating coordinate system. So what's the velocity vector? Apply this formula. So the position vector is what I'm going to call P. This velocity vector is equal to, a time derivative, total time derivative of P. And that's equal to the time derivatives of the components. That's what we're used to thinking of as the velocity vector. But now we also have to account for those rotating axes. So we have plus capital Omega cross P. Or another way to say that is the velocity vector is equal to the velocity vector observed in the rotating coordinate system plus capital Omega cross P. Now the acceleration is equal to v dot And so that's equal to you can think of that as Vx dot, Vy dot, Vz dot plus capital Omega cross V, right? But now this V is ugly looking, so this is going to get more ugly looking. All right, so Vx dot, Vy dot, Vz dot is equal to, well, these are the components of V, right? And so if we're just taking time derivatives of the components, here's what we have to do. So first, time derivatives of the components of this vector just give you px double dot, py double dot, pz double dot. And now the time derivatives of the components of this, the correction term, give you capital Omega dot cross P plus product rule, capital Omega cross Px dot, Py dot, Pz dot. Okay. Well, that's only the first part of using this formula. Now we have to deal with the cross product of capital Omega with the position vector. Sorry, we're on this one. So cross product of capital Omega with the velocity vector. And this is the velocity vector. So we have that capital Omega cross V is equal to Omega cross Px dot, Py dot, Pz dot plus, so now we've dealt with Omega crossed with this term. Sorry, I keep using the wrong one. Omega, yeah, so now we're doing capital Omega crossed with the V vector. So we've done Omega crossed with this part. Now we have to do Omega crossed with this part. So that's just Omega crossed with the quantity Omega cross P. And now put that all together, and you get that the acceleration vector is equal to Px double dot, Py double dot, Pz double dot, plus Omega dot cross P plus Omega cross the vector Px dot, Py dot, Pz dot plus another one of those same things, Omega cross Px dot, Py dot, Pz dot plus Omega cross quantity Omega cross P. And we can simplify one thing with these two. So we get that acceleration is equal to px double dot, py double dot, pz double dot, plus omega dot cross p, plus 2 times omega crossed with px dot, py dot, pz dot, plus omega cross quantity omega cross p. Or another way to say that is that the acceleration is equal to, this term is the acceleration that's observed in that rotating coordinate system. Plus omega dot cross p plus 2 times omega crossed with the velocity that's observed in the rotating coordinate system plus omega cross quantity omega cross p. Okay, 2 ways to think about it. All right, well, let's stop there. So I'm going to start next class. First, I'm going to compare this to the expression we have compared to the watermelon equation, because a lot of these terms look the same, and that makes it easy to confuse these two. Like, what are you talking about when? So I want to talk about that a little bit, and then I'm going to go back to that astronaut example, and we'll actually do some calculations, and we'll do it 3 different ways. We'll do it with a coordinate system mounted on the chair of the astronaut, a coordinate system mounted at the axis but rotating with the astronaut, and one mounted fixed at the axis and watching the astronaut go by. And if it works, they all need to give us the same thing.